So the Lewis definition of acids. We've talked about Bronsted-Lowry and Arrhenius. The Lewis model focuses on transfer of an electron pair. Lewis electron dot structures. We're all looking at Lewis electron dots. So in the Lewis definition of an acid is an electron pair acceptor. A base is an electron pair donor. That's opposite of hydrogen because hydrogen and electrons are kind of opposite of each other, right? So the Bronsted-Lowry looks at the proton that's being donated, and the Lewis model looks at the electron pair. So H+ is acting as a Lewis acid because it's accepting this electron pair from the nitrogen. So, hey, we're going to share this electron pair. And H3 acts as a Lewis base because it's donating the electron pair to hydrogen. And why do we even talk about this? Well, the Lewis definition expands the substances that can be considered acids. So now you can have an acid that doesn't even have hydrogen in it. Oh no. They're not named as acids, if that makes you feel better, but they can act as acids. So here's boron trifluoride. Boron trifluoride has an empty orbital. That empty orbital can accept the lone pair on this nitrogen for ammonia. Ammonia acts as the Lewis base, BF3 as the Lewis acid, and they get together, they form an adduct. So these two molecules come together, they're called an adduct.
Now, why did it rearrange so that the chloride is in the back of the boron, isn't it?
Well, because the boron is what has the empty orbitals.
Okay.
And it looks weird if we write it as F3b, because that's just not how we write it.
Right.
But it's the boron and the nitrogen that are going to get together. The boron's going to accept the electron pair. The nitrogen's going to donate the electron pair. So basically, I really need to stop using that word. A Lewis acid is going to have an empty orbital or is able to rearrange electrons to create an empty orbital that can accept an electron pair. Yes?
To know that it has an empty orbital, do you have to know the Lewis laws to put it on?
One way to know that it has an empty orbital is to look at the Lewis structure, yeah. Because if we look at the Lewis structure for BF3, not with the highlighter, although that did work better than writing with the eraser. I do that a lot. The good thing is people can't tell when I do it because it's invisible. So boron trifluoride, this is one of those molecules that violates the octet rule. Here boron only has 6 electrons instead of 8. So it has an empty orbital. And so this can get together with that lone pair on the nitrogen, and they can stick together, basically. Yes, it only has 3 bonds. Because the octet rule. 8 is good.
But that's not a part of the octet until now.
Well, so boron does often violate the octet rule, but it often reacts in a way to complete its octet. So it's not that it's super happy about having 6, but it'll tolerate it, if that makes you feel better.
Why doesn't it BF4? I feel like there's a reason why I just can't remember why.
Well, BF4 would have an odd number of electrons. Boron's not actually... Yeah, it just doesn't work out. Try drawing the Lewis structure. It doesn't work. So molecules that have incomplete octets, like the BF3, can act as Lewis acids. So here we have aluminum chloride, AlCl3, and here the aluminum has an incomplete octet. So it can accept this pair of electrons from the nitrogen. This is acting as the acid that's acting as the base. Here we've got boron trichloride, and here we have diethyl ether. So either you get it or you don't. The oxygen has 2 lone pairs, and so these lone pairs are the base part, right? So this can act as the base, and here we've got boron with an incomplete octet, so the boron can come over here, and now it has a complete octet. It's formed an adduct. Any questions? This is the kind of acid-base stuff that happens in organic chemistry. And then you get the ones that can rearrange themselves. Yeah, right? So this is like a classic OChem thing with we're drawing these curved arrows showing where the electrons are moving to and from, and yeah.
Oh, because when it combines,
The electrons rearrange when these two combine. And so a lone pair from the oxygen can come and be donated to the carbon, but the carbon wouldn't have room for that, so it shoves one of these electron pairs off onto the oxygen here, and so then we get this thing in the middle. And the lone pair from this oxygen comes over and is sharing with this hydrogen, and the hydrogen's like, I like this oxygen better, and so this lone pair goes over here, and we end up with this, carbonic acid.
Why is hydrogen like the other oxygen?
That's a good question. Why would it do that? That's beyond the scope of this class.
Okay.
But carbon dioxide acts as a Lewis acid. So I often forget to do this, but when we do titrations and you get that nice pale pink color, if you take a straw and blow bubbles into the solution, the carbon dioxide in your breath forms carbonic acid, which neutralizes some of the sodium hydroxide, and you can make the pink color go away. It's not, it won't solve the problem of I went over the endpoint. So it's not actually useful, but it's a great little trick. Yeah.
in that case, you would add like not even half a drop, and then it would probably turn pink relatively easily. Or
Well, it would turn pink really quickly by adding more sodium hydroxide, but the bigger problem is you don't know how much carbonic acid you made when you blew into it. So it's not really quantitative anymore. But how much of the carbon dioxide from the bubbles that you made actually went into the water, and how much of it just came straight out? And it's easier just to do another trial. There's a lot of things that we could do, but it's not worth doing. Okay, so we talked about these small, highly charged cations. These are acting as Lewis acids. So here we have an aluminum 3+ ion. It's got empty orbitals because it lost some electrons. So here we have water, which can act as a Lewis base. The oxygen has a lone pair. It can donate a lone pair to the aluminum and form an adduct between aluminum and water.